Okay, so welcome to lecture 4. So let me just take few moments so that things don't appear disjointed. Ultimately, I'll tell you what we are trying to do. We are trying to get to understand real E versus K diagram, and you will notice that I've been stressing this conductivity business, how conduction happens, etc. You think sort of is a little bit side business, but of course important. But all along in trying to explain that, we are developing some ideas. I have shown you K vector, origin of K vector in free electron theory, which is a wave vector. I have shown you that this K vector also means momentum. We have energy versus K relationship. We want to plot this EK diagram. Eventually, as we go along, I will show you that EK diagram contains all the information you require for electron dynamics. It tells us the properties of material. It tells us whether it's a good optical material, which is what the subject of this course is, or it is not, how things become the semiconductors, etc., are all connected to this, which we will be covering in this course. So ultimately, or at this point of time, my goal is to make sure that you understand what EK diagram is. When I show you the real EK diagram, it will be a complicated, messy diagram. In next, therefore, 2-3 lectures or 4 lectures, what I'm going to do is slowly build up the case which explains what is the justification for drawing the real EK diagram, which I will be showing you a little bit later. Interim, which I am trying to build up through conductivity, understanding of why we are introducing each idea. We have gone up to free electron theory, and we have shown you that free electron theory does not explain everything because it does not have an idea of lattice underneath. So what we are going to do is now explain lattice. Given a lattice, I will show you that I will also explain reciprocal lattice, and its sole purpose would, or main purpose would be that you will see that this K vector lies in reciprocal space. Its dimension is inverse of length. So imagine a space in which all the scales are in inverse of length. So reciprocal lattice vectors would lie in that space, and they will play an important role, and that role I will show you. That the role reciprocal lattice vectors, not the reciprocal lattice by itself, but reciprocal lattice vectors which we will have, will be useful in constructing the EK diagram. That is why we want to introduce these two ideas at this point of time. Eventually what I will do is, and remember in free electron theory, we also did not put any potential. We said it is free electron. That means it does not see other ions, it does not see any potential. Because of that, we made the V term equal to 0. But eventually, really that is not correct. Because there is a underlying lattice, we should have a potential, and that potential should be periodic, having periodicity of the lattice. We will have to introduce that, and when we introduce that, some remarkable things will happen, and you will be able to understand why some materials are metal, why some materials are insulator, and why some materials are semiconductor, which free electron theory cannot do. Remember, it is really good for only metals, but because metals is where there is a hope for electron to be free electron. Other places it will not be free electron, and there you will start seeing the semiconducting behavior also. So that is the reason we are trying to move in this direction, and this lattice and crystal structure and reciprocal lattice is a review. I am just going to review so that I take along all the students, but I expect most of you to have seen this before. So therefore, I will go a little fast and only pick in the relevant portion. So this is a review to this lecture number 4 is a review lecture on lattice and crystal structure and reciprocal lattice. I will just take the fundamentals here and not great details in here. Okay, so this will be a dialogue. This will be more of a question asked, answer given, question asked, answer given. That is how we will produce, that is how we will move along on these two topics today. All right, so let us do that. So first question asked, what is a point lattice? That is the first question we are going to ask. What is a point lattice? Well, point lattice, remember first what is a lattice or point lattice? First of all, remember lattice is not crystal structure, lattice is imaginary array of points. It is just imaginary array of points. You think of points arranged in space, you think of, not actually put something there, but you just think of them as some points in space. Let me give you an example. Let us say here, here are some points. Let me draw these points somewhere here, like this, like this, like this, like this, like this, etc. We draw something like this. What do you see? What you see is that if each point, if you take any point and that point looks identical, if I take this point and I stand here and look in particular direction and then I move out and I see my environment, how the environment looks like. If we go to another point, let us say this point, and look in the same direction as I was looking from here, and I find exactly same environment, same arrangement of points around here, that means each point in this imaginary point is an indistinguishable point. Any direction you look at on any point, I mean you look at particular direction, not that you can in each direction the view is same, in each direction the view may be different, but if you pick a direction, then you stand on any point, you will see the same view, the arrangement of points will look the same. That is really the definition of point lattice. So, this is a example of point lattice, where if you stand here, then you see something of a, you can see this is the orientation. If you stand here, you see the same orientation. If you stand here, you see the same orientation. You see the same orientation at this point, any of these points, you see the same arrangement of points. If you see here, you see a point here. If you stand here, you see a corresponding point here. If you stay here, you see a corresponding similar point here. If you stand here, then you see a corresponding similar point right here. From here to here, from here to here, or from here to here. You see some points are they are identical points. The orientation is identical. A counter example may be arrangement of points, which is something like this. Let me see if I can draw a nice picture. I will attempt to first draw some pictures, not the points. I will draw some pictures. Just hold on for a minute with me, and then we will see. I will give you example where which will not be a point lattice. Okay, now I think you can safely assume what I am trying to draw, and hence continuously imagine this and think of these as the points, these imaginary array of points. So, remember, not all regular arrangement lead to point lattice. That example you can see from here. It is a nice regular arrangement of points, which you can see. This is a beautiful arrangement, but notice that if you pick this particular location, if you see, then you see a atom in this or a point in this direction, not atom, a point in this direction, you see a point in this direction. But if you stand somewhere else, another point, let us say you stand at this point, what do you see? In this case, there is a lattice point in this direction, there is a lattice point in this direction. Clearly, the red type of lattice point, this red lattice point is quite different, has a different environment from the lattice point, which is black in color. So, clearly you can see that this cannot be a point lattice, though it is a regular arrangement of points. Okay. So, that is one thing about the what I wanted to tell you. Then so point lattice, this is a point lattice, not a point lattice. Okay. So, now let us look at what are the symmetry elements which are underlying these point lattices. So, let us talk about symmetry . The four basic symmetry elements that can be seen in a point lattice. One is, of course, this reflection. That means, if you have let's say let's do an example. Let's say something like this. Imagine this lattice, and in this you imagine a plane which is looking something like this. Imagine this plane. Imagine this plane. About this plane, you can see that this point, about this plane, if you reflect this point, there is a lattice point. This kind of symmetry is about a plane. That is, if there is a mirror plane, that there is a mirror plane. So, I have drawn a red mirror plane such that one half coincides with the other half as mirror reflection. So, if every point which appears on this side, let us say this one, this point right here, if there is a mirror image of that always on the other side, and this is a reflection symmetry. Similarly, we can think of this rotation symmetry. This kind of symmetry is about an axis. So, let us try to draw an axis and show you in a cube what this would be. Let us say that we draw similarly a cube again. This is a cube. Let us look at some axes in this. Let us imagine an axis which runs like this. Right through the center, it runs like this. This is the axis. Imagine this axis right going through the center here and here. What do you see? You see a four-fold axis. If you rotate this 90 degrees, if you rotate 90 degrees, you will find that if you rotate 90 degrees, then you will find that this point reaches this point. 90 degree, if you rotate it 90 degree, the lattice looks the same. That is a rotation symmetry. Similarly, you can see a three-fold rotation axis. If you wish, I can show you a three-fold rotation axis along the body diagonal. So, if you look at this, take this point and this point, along these points, if I draw a body diagonal like this, and you notice, try rotating about this. This is a three-fold. If you rotate it around it, you will see a three-fold rotation axis. That means, if you rotate it around by 120 degrees, then you will generate basically the same structure essentially. So, this is therefore, it is called an n-fold axis, a three-fold axis and a four-fold axis I have shown you. So, there could be a two-fold axis, there could be three-fold axis, there could be four-fold axis, there could be six-fold axis, but there cannot be a five-fold axis. Think about that, quasi crystals or something you have to think about. Then another kind of symmetry element is inversion. That is, a point is an inversion center if every point on the lattice reproduces another lattice point equidistant from the inversion center on a line joining these two lattice points and also passing through the inversion center. So, you imagine like this, it's instead of a mirror plane, it is a mirror point. So, if I stand there in a corner in the center of the room, I look at one of the corners, and if I reflect about this point, if I perpendicular to this, if I reflect, or rather I should say, if I join these 2 points and continue the same distance in the other direction, then I will generate another point. If I do find a lattice point there, and this happens for all the points, then it is a inversion center. For example, let us draw one, again a cube, and show through a cube that inversion center in it. So, this is a cube I am drawing here, and let us say if we put an inversion center right in the center of it, then you imagine that I have a lattice point here. Then whatever the distance I start joining these 2 points, I join these 2 points, and I continue on this point an equal amount of distance what I have just drawn, and then if I do that and I find that I land up on another lattice position, and that should happen for all the points. A point is an inversion center, every point on the lattice reproduces another lattice point. So, every point should be able to do that. So, corresponding to this point, I will get another point here, corresponding to this point, I will get another point here, so on and so forth. So, this structure has a inversion symmetry. There is a point of inversion symmetry, inversion center in there. Okay. Rotation inversion, same idea. Essentially, it is a combination of rotation and inversion symmetry. This symmetry operation is a combination of rotation, that is, lattice is first lattice is reproduced. If you give a n-fold rotation, whatever the rotation axis is, n-fold rotation axis is, if you give a rotation, it may not match at this stage, but then there should be also inversion symmetry, and then if you use inversion symmetry, then you may be able to generate a lattice. Example, maybe I draw another example here through a cube for this case. So, this is this case, this is this case, this is this case. So, I draw another case, another thing right here. don't know how good this drawing will turn out to be, but nonetheless we are going to attempt. A cube, for example, let us say center right here, here is the center, and let us draw a, remember the four-fold rotation axis, a four-fold rotation axis, and this is also an inversion center. So, this is the inversion center and this is a four-fold rotation axis. So, let us trace a point. What happens? Let us say that I have a point right here. So, I have a point here. Now, what do we want to do? That we want to produce a n-fold rotation. So, four-fold rotation we are going to do this about this axis. About this axis, when I do a four-fold rotation, I go rotation like this, 90 degrees I do. So, then where do I reach? Let me show you by this color. So, we reach here. We reach here. I reach here. This may be lattice point. This may not be lattice point. Does not matter. But after that, we do a inversion symmetry and then I reproduce the about this point inversion symmetry. Then I reach this point right here. Now, you see what this says, that is that if you have a lattice point here, then a system, if it has rotation inversion symmetry, then you would have a lattice point here also, and here also. That is the rotation inversion symmetry operation as far as this is concerned. All right. So, these are there is the point lattice. Underlying this point lattice are these therefore symmetry elements. With these symmetry elements, now let me define one more thing before I second question is what is a unit cell. Third question is what is a unit cell. What is a unit cell? So, now we know that there is a periodic, it is a point lattice is a periodic lattice, the underlying symmetry elements. So, based on periodicity of the lattice, if you choose 3 vectors, non-collinear vectors, then in that case not all in same plane, then I can describe those 3 lattice vectors by A1, A2 and A3 as 3 vectors. Sometimes use A, B, C, does not matter, A1, A2, A3 as the 3 vectors. Then I should be able to find position vectors. I should be able to position vectors of the points by R vector called N1 A1 plus N2 A2 plus N3 A3. That means, I should be able to reproduce all the points by taking N1 N2 integers, N1 N2 N3 integers, these are integers. So, I can take this and I should be able to get to another point. This is one way to look at it. Second thing is, other way to look at it is that A1, A2, A3, since the 3 non-collinear vectors, they are not, therefore, they will construct a volume. Whatever the volume is, if you translate this by distances A1, A2 and A3, then you should be able to fill up the complete space generating those lattice points. These are 2 ways you can think of unit cells. All right. So, there is a requirement of translation. That means, you translate, I will give you 2-dimensional example that will make things a little bit clear. For example, let us say I have something, a 2-dimensional lattice, and you imagine this in 3 dimension, something like this. In fact, let me make it a little bit more complicated than I am drawing here. Let us say like this. Okay. So, something like this, suppose this is a lattice, I choose this to be, or use different color here. So, let us say this is what I choose as my unit cell, which this is A1 vector, this is A2 vector, let us say this is A1 vector and A2 vector right here, like this here. So, A1, A2 vector define this area. Now, you notice that if I move this A1, whatever area is constructed by A1, A2, we keep moving, we can generate all these lattice points, right. That is what is implied by a unit cell. So, this is a good unit cell. Now, so 3 vectors A1, A2, A3. So, A1, A2, A3 define a unit cell. They define a unit cell. They are not necessarily the smallest volume, which we will see. by changing the angles or distances, size of magnitude of A1, A2, A3 or the angles between them, there are 7 types of, and this is something you know, this is 7 types of unit cells are possible: the cubic, the tetragonal, the orthorhombic, the rhombohedral. So, there is this cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic and triclinic, depending, and increasingly cubic system has the highest degree of symmetry elements and triclinic has the least number of symmetry elements inherent in them. So, now these unit cells, the way it works is in 1848 this French crystallographer, his name was Brevis, suggested based on the symmetry elements they can only be precisely 14 point lattices based on the symmetry in combination of what we have looked at point, what is definition of point lattice. Based on that definition of point lattice and the symmetry elements which are underlying these point lattice, they can be exactly 14 Brevis lattices. Those Brevis lattices have been drawn in this picture and you are quite familiar with it. Something is called there is a simple cubic, there is a body centered cubic, there is a face centered cubic, there is simple tetragonal, there is a body centered tetragonal, there is simple orthorhombic, body centered orthorhombic, base centered orthorhombic, face centered orthorhombic, rhombohedral, hexagonal, simple monoclinic, base centered monoclinic, triclinic. These are the 14 Brevis lattices which I have drawn on this page here. So far so good, and up to here I presume you all were very well versed. Now, the point I want to make now is where things start, and this is where you need to pay little bit attention, and because this is where we are going to be it may become slightly confusing for you, that is where. So, let us look at this. Let me do this, that if I take, there is no fundamental way, there is no requirement. Let us take example. Let us take an example like this in 2 dimension again. The choice of unit cell is yours, how you choose your unit cell. For example, a person may choose the unit cell like this based on this A1 and A2 vector, and you can always imagine the third one also in 3 dimension. It is easier for me to draw in 2 dimension. Another person may choose that no, they are going to use this one as A1 vector and this as A2 vector, which will in this case define a volume area which is like this. Will define an area which is like this. Another person may choose something different, in the sense that exactly opposite. They may choose these to be to the vectors A1 and A2. Let us say this is A1, this is A2, in which case this structure will now look like, this unit cell will look something like this. All these are perfectly good unit cells, and you notice their space filling. You translate them along directions of A1 and A2, multiples of integers. You translate them by, that means by, if you move by change A1 by integer or A2 by integer, you will translate by that amount, then you will fill the space and generate the lattice, and does not matter which unit cell you choose. There is no unique choice of of these lattice vectors. You are free to choose the way you want to choose. Of course, there is a simpler way of choosing and there is a difficult way of choosing, which is why you see normally people choose like this, which shows the square symmetry of this lattice. Though this particular, this for example, this or this lattice has exactly same symmetry, but for a person looking at it, it looks like a rhombus or a parallelogram, something like that. It looks like these unit cells look like a parallelogram or a rhombus. They do not show symmetry of a square type lattice. Sorry, they have a, yes, it is not the square type. Symmetry is not obvious, whereas that underlying symmetry indeed does exist, because it is the same lattice after all. So, the choice of vectors you make is your choice. Sometimes some choices will make things easier, and sometimes they are difficult. Nonetheless, let me now move on and try to explain another aspect, what is what we will be interested in, and next topic therefore will be what is a, next question would be what is a what is a primitive cell. Okay, so now let us take this by example. Now notice that when we looked at cubic, if you looked at cubic, it came in 3 versions: simple cubic, let me draw one more cube first. For example, cubic lattice come in 3 versions: lattice points, not atomic positions yet, no atoms, just imaginary lattice points here, or here, 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 and one in the center, or in these corners, and also face centers, and one in the front face. This is of course face centered cubic, this is a body centered cubic, and this is simple cubic. Notice that how many lattice points we have per unit cell. In this cell with atoms or lattice points only at the corners, I have 1 lattice point per cell, which means this is in this case we call this as primitive cell, you will recall that. And then there is a body centered has 2, this has 1 point, this has 2 points per unit cell, and this has 4 lattice points per unit cell. So, definition of a primitive cell is 1 lattice point per unit cell. If you have 1 lattice point per unit cell, then it is called a primitive lattice. Clearly, simple cubic is the body centered cubic as shown, the unit cell shown is not a primitive unit cell. FCC as shown here is not a primitive cell, but it is always possible to make a primitive cell out of any structure. Now, if I have a BCC or I have a FCC, I still need a primitive cell. It is always possible to do so, and I will show you some. I will show you by some example. Let us assume, consider BCC lattice. Let us choose vectors as A1 as a x hat, A2 as a y hat, A3 as a by 2, a being the lattice parameter, edge length of all these, plus y plus z. Let us choose these as lattice vectors. What does it look like? Let me draw it for you, and then it might become a little bit clearer for you. So, let us assume that it is something like this. Let us assume this cube to be like this. This is a BCC. Now, if you choose your lattice vectors as follows, you choose, let me use another color now, use this as A1, you choose this as A1, you choose this as A2, this is A1, and you choose one in the center, there is an atom in the center, you choose that as A3. So, what I am going to do is, I am going to draw an axis also. So, if you take an axis like this, x, y, so this is the y axis, this is the x direction, and this is the z direction. Then remember, what is A1? A1 is a times in x direction. So, I am choosing this as A1, this as A1, and A2 is in y direction. So, I am choosing this as A2, and then third center point, the body center point is selected as the A3 vector, which is this vector. Now, this is A3, this is the A3 vector. So, if I choose the vectors to be like this, now you can notice that that whatever these 3 vectors will generate will be a volume which will not look like a cube, but it will be, since the lattice points will be only at the corners of this vector, therefore, it will become a primitive vector, primitive unit cell, which will be defined by A1, A2 and A3. If you wish, you can find the volume of this, we can find the volume of this particular through the enclosed by these vectors by taking a scalar product of it, and you will find that this volume is half the volume of A cube. If we take BCC like this, then the volume will here be A cube, of course, and if you calculate from here the scalar product, you will find the volume to be A cube by 2, because now I have only one lattice point per unit volume. There will be half the volume only. Let me take another choice of lattice vectors. So, set 1. So, this is set 1. Let us take set 2. Let us say A1, choose something like this, A by 2 y hat plus z hat minus x hat, A2 as equal to A by 2 z hat plus x hat minus y hat, and A3 as vector A by 2 x hat plus y hat minus z hat. Let us suppose you choose vectors like this. You want to see this one? Let me draw this also for you and show you how this one would look like, how these vectors would look like. Keep this big enough. I am trying to draw a cube, though it does not look like exactly a cube, but nonetheless bear with me and use little bit of imagination also in here, only then it will probably work. So, I have point here, 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 point here, point here, lattice point here, and one lattice point of course is there in the center also. There is lattice point in the center also. But now notice what I have done. What I have done is that if you choose, let us say, let us choose our axis. So, that this is x, this is x, this is y, and this is z going up z. Suppose this is the y direction, this is the y direction, this is the x direction, and this is the z direction, is how we are pursuing on this. Okay. So, if this is the case, let us draw this. How do these vectors look like? What you will find is, remember, there are always going to be a point. There is another going to they are going to be, let me draw with blue ink probably. There is going to be another body centered point right here, which belongs to another unit cell, which comes out like this, which is there is another unit cell which comes like this. Maybe this drawing is getting messy. So, we remove this, all this, and I will leave this to your imagination actually. So, probably easier that way. Okay. So, let us do this. Let us do it this way, that you imagine that there is a unit cell right here, another unit cell which continues here. On this, you consider this face, and out of this face further you see another unit cell. At the center of it would be another lattice point. So, that lattice point I am going to draw right here. I am going to draw that lattice point right here. Similarly, and this lattice point when joined with this, you can see this vector is A1 vector. A1 vector. That means, on the y and the z face center point, but in x face, in x direction go negative direction, and if you go in negative direction, that means you are coming out of this face, and you will find a lattice point. Similarly, on A2 for A2 vector, what you do is do the same thing. You look at the z and x face, and then you go out of that cell, and out of cell z and the face which is formed by z. This particular, you will imagine this particular plane. This is z x face, which is now given by z and x and minus y. In y direction, you move in half the distance in y direction. So, if you do that direction, then you locate this point outside on this face, a body center point. Similarly, in this case for A3 vector, you see x and y plane, the bottom plane. You take the bottom plane and go down further below. So, this will be your A2 vector, this will be A2 vector, and going down below there will be the A3 vector. This is bad, sort of little bit bad drawing, but if you draw this particular then what you will have is, now you can imagine, if you wish, there is a BCC cell. In this BCC cell, you can think like this. There is a lattice point which has been taken. Now, if you, the unit cell will look much more like this one. This is how the unit cell will look like, the shaded one. You can imagine this to be in context. Let us see, if you've taken the center to be somewhere here, then you can go one out. This cell, you can see unit cell is in 3 directions coming out, and this clearly does not look like a body centered. If you take this lattice vectors, then this is how you have to little bit do imagination. This is how the unit cell looks like, and if the unit cell looks like this, and its volume again will be half of what A cube is, because now they are only going to be only one lattice point per unit cell. And where are those lattice points? Those lattice points will only be at the corners. These are going to be the lattice points, and therefore, you can clearly see that this is a primitive unit cell. So, it is always possible to make a primitive unit cell out of any, whether it is BCC, FCC or any cell. It is always possible to make a primitive cell, and there is no unique way of making primitive cell. For case of BCC, I have shown you 2 ways of making primitive cell, and eventually you will see we will use this particular definition of lattice vectors for primitive cell. Okay, so now this BCC primitive cell I have shown you. I mean, I have given you this set 2 vectors here, right here, and I have shown you the structure of it. You try, please try drawing it yourself, because it does not quite look so nice, but nonetheless, believe me, it is proper BCC cell. Does not show BCC symmetry, which is why it is BCC always drawn some different way, but it is always possible to make a primitive cell like this. And these primitive cells are the ones which we use in analysis. So, these are the vectors which we will use. I promise in case of FCC, I will show you a little bit better picture. Okay, let us use FCC. FCC, now you see FCC has 4 lattice point per unit cell. So, let us see how that looks like. Let me first give the cell lattice vectors to you. Let us say A1 choice I make. One way is, of course, you make A1, A2, A3 as conventional null cell will have A1 as A times X, A2 as A Y, and A3 as A Z, which is same for BCC also, just that there is a point at the face centers also in this case, right. And you construct a unit cell using this and use that as a repeating unit, then you can generate FCC, and with having 4 lattice point per unit cell. But primitive cell, let us construct a primitive cell. Let me show you how one can make a primitive cell from FCC also. By choosing, let us say I choose A1 as equal to A by 2 y hat z, and A2 as equal to A by 2 z, and A3 as equal to A by 2 x plus y. So, you choose our primitive cell like this. Let me draw this for you this time a little bit better. So, here I have shown you, I am going to move here and show you this unit cell first. So, here is a FCC unit cell, a cube, and this red points which you see here are the corner points, and as we go along, I have shown you 2 FCC, and then I have shown you 3 FCC points, one blue, one green, and one yellow, and I am going to show you, and I have not shown the other on this face. This particular face is the blue point. These 3 points I have shown the face centered points, but I have not shown you face center points on other places, just so that the figure does not go start looking bad. So, that is nonetheless you can imagine those points. So, let me move back here and let me draw these vectors for you. So, if I choose my orientation, if I choose my origin to be like this, so if I choose my z to be like this direction, or I make it from here itself. So, I do it like this, z is this direction, and this direction as I have drawn it, and one direction here, then this is x direction, and this is y direction, and this is z direction. Accordingly, let us see now what A1 is. If I look at A1, so A1 will correspond to my blue. So, if I take A1 is in y and z plane. So, if I take this blue plane, right here, this is the blue plane here, this particular plane and the face center of it. So, therefore, this is the A1 vector. So, this is the A1 vector, and now if I look at the A2 vector is in Z and X plane, So, that is the one which will be given by this green stuff. So, let me draw the green one. So, if I consider this plane, this front plane, if I consider this front plane, then I can construct this vector. This is the face center point of this on this plane. This is A2 vector, and similarly, if I take the bottom plane A3, where it is in XY plane. So, if I take this one, then it is on the yellow plane. So, if I take this bottom plane right here, if I take this bottom plane, and in the face center point is right here, then this is A3. This is A3. Now, see what does it construct? What do you get? These three. If I choose these three vectors, what do I get? What you can get now is I am showing you the three vectors as these are the three vectors right here. This one, and this one are those three vectors. If you have these are the three vectors and you construct a volume out of it, then you get a nice structure like this, which is shown here, and you can see that this is a primitive cell with lattice points right here, 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 right here. Of course, these two, let me use another pen. This point and this point are the two corner points of this FCC lattice, which may be marked red. I mark them in this red. Rest of the points are all face centered points. Rest of the points are all face centered points. This on the top, the face center point on the bottom. Here the face center on the front. Here the face center point in the back. Here the face center on the right. Here the face center point on the left. So, these are the face centered points. Now, if you calculate the volume of this cell, it will be exactly 1/4 of A cube. A cube was a conventional cell, which with a volume of whole cube had a volume of A cube, but since this is, and that would have 4 lattice point per unit volume. If you now calculate the scalar using the scalar product of these three vectors, you calculate the volume, you will get 1/4 the volume. But this is a nice primitive cell. Before I end on this subject on primitive cell, then I ask you I show you another kind of primitive cell, which is called as Wigner seed cell. So, last topic in this crystal structures is this Wigner seed cell. Another way of making a primitive lattice is as follows. Take for example, this BCC. Take this as primitive cell. This is also a primitive cell. Let me first make it in 2 dimension, maybe to show you to make the point. Suppose I take a square lattice in 2 dimension like this, and instead of choosing a primitive lattice like this, primitive unit cell in 2 dimension like this, which I could, another way to choose this will be like this, and this particular cell which I have shown you by red right here has 1 lattice point per cell, because lattice points are only in the corner. If I take this one, I can choose another way of choosing a lattice point is like this. If I choose my unit cell to be like this, if I choose the unit cell to be like this, notice this also has only 1 lattice point. Now, the lattice points are not at the corner, but this is also a repeating unit. If I repeat this unit, I generate the whole. This is also a good unit cell. This only lattice point is in the center. There is no other lattice point, and this is also a primitive lattice cell, the primitive unit cell, because it has 1 lattice point per unit cell. Exactly same thing can be done for different crystal structures. For example, take this BCC example. Imagine this to be 1 cube. Here is 1 cube. Take this 1 cube here, right here. Take this one particular cube here. Take this 1 cube. Now, if you know that you have a 1 lattice point right in the center. From that center, draw lines to all other lattice points, take perpendicular bisectors of them, and what is left then is this kind of structure which is shown here. You take perpendicular bisectors and find what is the smallest volume. so you from the center point you draw lines to all other lattice points, draw planes which are perpendicular, to these lines right in the center of the 2 point, whatever the line is joining 2 lattice points, right in the center of it or center of this line, draw a perpendicular plane. Keep drawing it like this for all the lines you can possibly draw, and construct the smallest volume. And construct the smallest volume in case of BCC, clearly as the geometry shows you, that if I have a center, let us take example, I have a center point, here is this line, and this is the perpendicular bisector for it, there is a plane which is the perpendicular bisector for it, which intersects at this particular point here, and then I make the smallest volume like this, then what you have is a primitive cell, because the only thing which is in there is a one point in the center, and that is called a Wigner seed cell. Similarly, it is done here for FCC. You can now imagine that on this face conventional cell, this is the one of the face of the cube. On this face, right in the center will be a face centered point. From this face center point, you draw perpendicular bisectors to all other points which are there. For example, you draw from here a perpendicular bisector to the top face like this, and it intersects here, and construct this plane, and on this plane it intersects right here, and in this way you construct this particular volume. This is also Wigner seed cell. Right in the center is a lattice point. Why am I talking about this particular cell? Because this will become a interesting point. This is precisely the kind of cell we will be looking for in reciprocal lattice. Okay, so with this I would like to close the chapter on this crystal structures or lattices. But last point, maybe I should say what is crystal structure, because I have not said crystal structure, that I will not go through, but crystal structure is simply lattice plus a basis. That means on all the lattice points which you have, you start putting now atoms, and whatever the basis is, one single atom, two atoms, multiple atoms, whichever you want to put it, that generates a crystal structure. And I will advise you that please brush up your knowledge on these crystal structures, and also look at also brush up a little bit on the directions and planes in these crystal structures, which we will frequently use and you may be useful. But in the summary, what we want to do is, in summary, there is a point lattice, there is underlying symmetry in the point lattice. Based on that, there are exactly 14 Brevis lattices possible. Some are primitive, some are not primitive. Whichever are not primitive, it is always possible to make a primitive lattice. Primitive lattice has one lattice point per unit cell, and primitive lattices are often used in analysis, which we will do. Shown here is for BCC, then shown here is for FCC, a primitive lattice. But there is another construct for primitive cell, which is a Wigner seed cell. This Wigner seed cell here may not be too much of importance, at least for us, but this will become same construction in reciprocal space would become lot more important. So this is where I would like to finish the topic of crystal structures and move on to what is called as reciprocal lattice now. Introduce this topic and then finish in the next lecture. So here is reciprocal lattice. Let us start with this. So now notice a direct lattice. We will use the word direct lattice. In contrast, we have a direct lattice. What we just did was direct lattice. So for this direct lattice, I will write a lattice vector R, which is we will use the symbol N1 A1 plus N2 A2 plus N3 A3, and I will always use a primitive lattice, which means, let us go back for BCC, let us go back and look at this BCC. That means I am going to use A1, A2 and A3 like here. I will choose A1, A2, A3. Similarly, if I take in FCC, I will choose my lattice vectors A1, A2, A3 to be like this. If I choose my lattice vectors in this fashion, I generate this structure. And remember, in this case, if I change N1, N2 and N3 like I am drawing here, if I choose values of N1, N2, N3, I will all integer values of N1, N2 and N3 with this choice of A1, A2 and A3. since it is primitive, because the points lie only on the corner of the unit cell, on the corners of the unit cell, therefore, by choosing n1, n2 and n3, this is a lattice vector by which I can generate all the lattice points by choosing n1, n2 and n3. If I choose n1, n2, n3 as 0, then all 0, then I start with some point, that is a lattice point, and then I keep choosing n1 equal to 1, n2 0, n3, I will get another lattice point, and I will keep doing. If it is not primitive cell, then you will not be able to generate all the lattice point by choosing n1, n2, n3 as integers. But because it is primitive cell, then R is truly a lattice vector which will generate all the lattice points. Now, similarly, I am going to do is, I am going to just write some expressions, some vectors now. First, I am going to do is this, I am going to write B1 vector, which I am going to write 2 pi divided by multiplied by A3 cross product of A2 and A3 divided by volume of, I will show you what volume of a primitive cell of this particular primitive cell. I will write B2 vector, just do not worry, just think there is something being written. What it is, I will see what it is. A3 into A1 cross product divided by same Vp, and I will write B3 as equal to 2 pi by Vp, volume of this A1 cross A2, I am going to just write it like this, and I am going to construct a vector called K, this vector as M1 B1 plus M2 B2 plus M3 B3. In fact, let me write this as succinctly as Ni Ai, and this as therefore Mi Bi, where I of course is 1 2 3, I is 1 2 3 only. All right. So, this is K vector I am writing, and Vp in this case is, and the Vp is just the scalar product A1 dot A2 cross A3 is the scalar product which gives me the volume of the primitive cell. So, if I take, so if I ask what is the primitive cell constructed by, if I construct a primitive cell with this vector A1, A2, A3 are vectors which construct the primitive cell, one wants to know what is the volume of the primitive cell in the direct lattice, then this volume is just simply this quantity Vp, volume of the primitive cell. So, I have divided this by volume of primitive cell, and then I generate a vector called K based on this, where M1, M2, M3 now are integers. What happens and why are we doing this is basically the story, what it means. Recall our wave function had a form of e to power j k dot r. That is the form. Recall the wave function which we had derived in free electron theory had this form, right, and also I mean this is a plane wave form essentially. Now, what we want is that phi of r, what we want is that e to power j k r dot product r plus r should become equal to e to power j k dot r. Why? See, this represents the periodicity of the lattice, that in the lattice if you move by this vector r, then you essentially are at the same point. This is the definition of point lattice, remember. So, if you move from one point to another point by this translation vector r, then the lattice looks identical, there is no difference in it. So, and then since we are going to deal with properties in this kind of lattice, then since these points are not different, they are identical, then the behavior of anything should also look similar. So, if my wave function has this form, then it should also acquire same character at those some special points. So, this is why we want that this to happen, because that we want that there should be periodicity of r in wave function also, which can happen only if you can see that means e to power j k dot r should be equal to 1. small k I have drawn, let me erase this, small k dot r should be equal to 1. If this happens, then this will be true, then this particular thing will be true in there. All right. Now notice, for all k's which are like our capital K which we have just derived, here is the capital K, here is the capital K which we have just derived, and this capital K which we have just derived, if we substitute this particular capital K for all small k's in here equal to this capital K, this is indeed true. This is indeed true. So, that is what essentially we would like to do here, that if you for some special values of k remember is a reciprocal space. Now, if you look at the dimension of this quantity B1, B2 and B3, then it is also inverse of length. Remember, A2 cross A3 divided by a volume. So, therefore, that is also inverse of length. So, the k clearly, small k clearly, this capital K vector clearly belongs to a reciprocal space, as do our this small k vector indeed belongs to the small k vector, you know, it belongs to reciprocal space, and so does capital K. If these two become equal, then this relationship which is shown here becomes true. So, this is the reason why we have generated this k vector in a form as we have, and you please try that. You substitute in here in this expression, substitute capital K in there and see indeed if it gets 1 or not by choosing B1, B2, B3 as we have. That is a small part of the story, but if you are familiar with this, you can see that if this is true in the plane waves, I can form a complete set, I can do a Fourier analysis, and for all periodic functions I would be able to do Fourier analysis. Any function which has periodicity of capital R, then I would, in this case, this is a really good set to do Fourier analysis. That is essentially what it means, but I will not, and that is what we do for X-ray diffractions, etc. But in this course we will not go through it. We will just, since my intention is to show you what is consequence, how to represent EK diagram, so I will limit my discussion only to that. We will continue on this part, since now I have constructed B1, B2, B3 as vectors, just like A1, A2, A3. A1, A2, A3 construct from A1, A2, A3 we could construct a primitive lattice. Similarly, with B1, B2, B3, these vectors in reciprocal space we should be able to construct another set of lattice in reciprocal lattice, and those we will call as reciprocal lattice constructed by B1, B2, B3, which we will start in the next lecture. Thank you.